Okay, so good morning. I would like to thank Wim for inviting me and for Christoph for organizing this nice conference. It's a pleasure to be here. I will speak about electronically excited states of molecular hydrogen. But first, let me just shortly introduce my background. I have a research group in Budapest. It's a theory group. We have two main directions. I come from rovibrational spectroscopy, and about 10 years ago, when I was a postdoc in Switzerland, I got to know fundamental molecular physics. I've heard about the nice experiments from Frederick Merck's laboratory and the wonderful computations from Christoph Pakutsky. So I got interested in this direction, fundamental molecular physics, and been following this direction of research since then. I soon realized that trying to understand NRQD from Christoph's papers is like trying to learn modern physics from the Landau series. But if you know what you're looking for, you will find it there, and it's correct. Okay, the past 10 years was enough to digest the literature, and I consider myself relatively fluent, at least up to M alpha 6. Okay, so so I will speak about the non-relativistic part of the hydrogen problem. The starting point is clear, and the context of my work really goes back to my years in Switzerland, and we consider the H2 problem as a four-body problem and look for a variational solution to the four-body Schrödinger equation. And my ansatz was an explicitly correlated Gaussian ansatz, and it was a global vector representation flavor, which I liked because my background is rovibrational spectroscopy, and it allowed us, at least in principle, to have a general and spatial quantum number. And actually the implementation, I was able to make the code stable up to n equals 5, 6. Okay, and with this background, I went through lots of H2 papers and realized that there was perhaps at that time less good agreement, and by now the agreement for the ground electronic state is even better. But I realized that there are many electronically excited states. There are lots of experiments on that, and the theory is much less developed in the electronically excited range. So I got interested in this, and I soon simplified the problem, or realized the problem that if we solve the four-body Schrödinger equation, then we basically can get these electronically excited rovibrational states as resonances of the full problem, and that seemed to be kind of an interesting theory problem, because the real variational principle that was used to compute the states of the ground electronic state was not really valid anymore for these rovibronic resonances. I don't have a general solution to this, but over the years we realized that if we are looking at a long-lived rovibronic resonance, then its basis function parametrization can be optimized, almost like using the real variational principle in a stabilization fashion. And using this procedure, we could select a few states in the sea of states of rovibronic resonances, the inner rotational states of the EF manifold, and we could improve on the existing theoretical results. So this was about solving the four-body problem. The non-relativistic term values are listed here up to n equals 5. We also computed the relativistic and QD corrections in this using the perturbative expressions everyone is using. We kept a relatively good agreement with experiments. So how does this pointer work? Okay. My tentative error bar is plus minus 0.005 wave number, so it's still much larger than what is currently possible for the ground electronic state, but this was an improvement. And Okay, thank you. So, we still had in mind is lots of experimental results for the electronically excited states of molecular hydrogen, and I asked myself whether we could have a systematic procedure to access any of them, or to compute possibly all rovibronic states in a given symmetry block. So for doing this, I take another look on the electron-nucleus problem. So if we write out really that we have electronic masses in the kinetic energy and nuclear masses in the kinetic energy operator, then nuclear masses are much larger than the electronic masses. And by writing, can you see? No, I need to show here. So this epsilon, the electron to some general nuclear mass ratios, is the small parameter that appears in the nuclear kinetic energy operator, electron kinetic energy plus interaction. And in short, so this is really the molecular Hamiltonian with the small parameter highlighted in epsilon squared. At the same time, we cannot assume that the nuclear kinetic energy is small, because we may look at highly excited rovibronic states. And we have the electronic Hamiltonian, okay, which depends on the nuclear position. So for the nuclear positions, I use big R, and for the electron positions, I use small r. Okay, so as an alternative to the direct four-body solution, people usually use sum of products of electronic and nuclear functions and write the molecular wave function written here. But it turns out that for spectroscopic purposes, I mean, the usual truncation of this number of included electronic state is not sufficient. So this ansatz converges slowly with respect to NL. So what can we do about that? Let's look at again the molecular Hamiltonian, highlighting the small parameter in the Hamiltonian. And as I said, so it appears in front of the differential operator for the nuclear coordinates. And of course, epsilon is small, but we cannot assume that the nuclear kinetic energy is small. So when this operator acts on the molecular wave function, then the result is not necessarily small. So when we do the perturbation theory, we need to count the epsilon orders according to this observation. But much of this was already known in the mathematical physics literature as phase adiabatic perturbation theory when I started to look at this problem. So, okay, so we have the electronic Hamiltonian. We can solve the electronic problem for different nuclear structures. So then we choose an electronic subspace and label it with P. And it's the only requirement is that it is electronic subspace. So the electronic states are separated by a finite energy gap from the rest of the electronic spectrum over the relevant nuclear configuration. So we partition the electron-nucleus Hamiltonian like this. So this is the usual partitioning. So we look at PHP, and eigenvalues of PHP are commonly used to approximate eigenvalues of H. But it turns out that eigenvalues of PHP have an order epsilon error there. Where epsilon is our small parameter. So can we improve upon the PHP truncation? And this is the strategy to do that. So instead of P, let's define some pi operator of N. Call it a tilted electronic subspace with some S operator, which needs to be defined according to this prescription. We would like to do this truncation of the electronic subspace, but we are looking for some operators which make the off-diagonal block that we neglect, or the epsilon smaller. And this is the recipe to determine A1, A2, AN, etc. And as a result, we get SNs. We will define an effective Hamiltonian for the quantum nuclear motion. And it's a unitary transformation of our partitioned operator, but this is just for convenience. The eigenvalues will be the same. So and we solve this effective Hamiltonian to really get the rovibronic energies that are sufficiently accurate. This procedure is reminiscent of perturbative techniques used in the rovibrational theory known as conjugate transformation, the relativistic theory known as Foley-Whiteson transformation. Of course, the actual operators are different. Electronic structure theory, I think it's known as von Fleck transformation. So, but we went through this procedure and got this the effective Hamiltonian, and the spectrum of this effective Hamiltonian will be better, provide a better approximation of H by construction and with an error of order epsilon n plus 1. This tilted electronic subspace, when we do the calculation, these S, so these A1, A2, etc. operators, turns out to depend not only on the nuclear positions, but also on the nuclear momentum. Okay, so the nuclei also move. And besides the usual terms in PHP, this effective operator contains corrections to the nuclear kinetic energy, and this can be interpreted as an effective nuclear mass. And so we dress our nuclei with some electron mass. Near the bottom of an electronic band, this mass contribution can be small, but as we excite the motion of the nuclei, so they have higher kinetic energy, it can be large. Okay, so these are the equations, but everything is in this paper. So I mean, I know it's difficult to capture so this is how this mass correction matrix looks like, and this appears in this effective Hamiltonian. So it looks like this, but I will tell you something more on it in a minute. For a single electronic state, it simplifies to the known expression. So this was known before, and the reduced resolvent for this, the particular electronic state appears in the expression. Okay, so for the single state expression was known. But it was often thought, at least this is how I understood for a long time, that you either do the single state mass correction or you do multi-state Born-Oppenheimer description. But in fact, you need to do, you can do both. So perturbatively correct for the neglected electronic states in a multi-state description. So we have expressions up to third order, but it appears to be practical to use up to second order. So this is the second order effective rovibronic Hamiltonian with the mass correction. So these other terms were known before, and this highlighted term accounts for the contribution, the effect of the neglected electronic states on the nuclear dynamics. And I mean, this is the interpretation. Nuclei can gain or lose mass, effective mass, as they pass along other distant electronic states. Okay, so this is kind of a recipe. Dominant, so choose a qualitatively correct electronic subspace and correct for the rest by there's a perturbation theory, and then different quantities appear. Non-adiabatic coupling vector, that's a vector. Then you'll have a scalar non-adiabatic correction and a tensorial mass correction. And it appears in the kinetic energy, and rovibrational computations are conveniently done in curvilinear coordinates. So we don't do in rectilinear coordinates, we transform the coordinate system to, I mean, for a diatomic to the stretching degree of freedom, for a triatomic bending and stretching. And so we transform the Laplace, so divgrad to curvilinear coordinates, and then there we will have to use the metric tensor and do the expressions. If we have a coordinate dependent mass, so this mass correction is coordinate dependent, so we have to transform div m grad. But okay. The other difficulty is that in this mass correction, we have a sum over state expression, sum over all neglected electronic state, discrete and continuous. So if we do explicit summation, we may miss the important part of the problem. But there are techniques, known techniques. This goes back to Hilaras, but it's also, it appears also in the evaluation of the beta logarithm, and the method is due to Schwartz, but they all boil down to defining a perturbed wave function, which captures the sum over state part of the problem. And this perturbed wave function is obtained by minimization of the functional. So this is known, and we adopted this this method due to Hilleros and Schwartz to this particular problem. For the ground state, it's relatively straightforward. For the excited states, it's also not too difficult, but we need to think about whether this functional is bounded from below or not. And then for an excited state, we may need to subtract the lower energy contributions and define the functional for the upper energy. So the infinitely, that's still infinitely many states contribute. Okay, for the ground state, for this, the mass corrections were computed by Paputsky and Komatra. We looked at electronically excited states. EF, okay, it's not qualitatively well described by a single state picture, but we still computed the mass corrections. We get a gigantic vibrational mass correction here due to this. The HH alter valve was known to be relatively well described by a single state description. There we computed the rotational and vibrational masses. The rotational mass is almost the same as the nuclear mass, but the vibrational mass correction is negative. So in this alter valve, the proton appears to be lighter than the nuclear proton, so the bare proton. So the effective mass is smaller than the nuclear proton mass. Okay, with this we did the computation, included the usual relativistic and QD corrections, the leading order both, and this resulted in an order of magnitude improvement. Okay, this is not particularly outstanding, I think, in this community. So how could we improve on this? Actually, the reason why we still have such a large error is due to the fact that if you look at this, it's in a sea of states. So it's amazing that a single state description works at all. So we need to do a multi-state non-adiabatic treatment. Okay, and this is rather more new. We have some preliminary results on evaluating the Vibronic mass correction for coupled electronic states of H2. Okay, so it looks like this. So here I separate the lower energy part and evaluate the higher energy part with the functional method. And that is then the functional is bounded from below. And these are the mass correction functions. Okay, it's relatively large here for the H state. So, okay, so this is the mass correction for the HH bar state. If I add 2 more states, then all the mass corrections get smaller, and I would say they are now in a reasonable range with respect to the electron mass. Okay, so it's just a few times of the electron mass. Okay, and we did so we solved the coupled Vibronic equation with the effective Vibronic masses. And here I show the deviation from experiment. Okay, this is not spectacularly good, but so the proton mass, the empty, the effective mass, filled circle, okay, still non-relativistic computations. We still work in progress, but okay, we can compare. We have a full non-Born Oppenheimer 4-body energy for this point. So if I use in the non-adiabatic computation the bare proton mass, I get a deviation from the exact 4-body energy and this in wave number. And if I use the effective mass, it's smaller. I don't have error bars, sorry. So it's just some preliminary work. So this is what I wanted to tell you and show you about the non-adiabatic problem related to electronically excited states of the hydrogen molecule. And I'm sorry, I would like to show a few more slides on a topic which we are very much interested in the group. This topic was discussed already a bit, relativistic theory. And I like to go back to do things differently. So we do an RQED, I mean, at least I'm for 5, so I should say Zuher theory or Araki-Zuher. But if Zuher actually started out from the beta Salpeter equation, 1951, which is a Lorentz covariant QD wave equation for bond state problems. It looks like this. So one electron propagator is the interaction, irreducible interaction function. But so the point is that Salpeter, 1951, Zuher, a few years later, derived from this beta Salpeter equation. This is a wave equation, exact equal time equation. It looks a bit more like a Schrödinger equation. Okay, it's 16 component, but it's a wave equation. So here, this phi is an equal time wave function. So it depends only on the spatial coordinates of the two particles, no relative time, no relative energy. This HC is actually this HDCB, which is the positive energy projected Dirac-Coulomb Wright operator, plus a correction term. And this correction term is complicated, but also includes an integral that depends on the relative energy of the two particles, the relative time. But okay, Zuher treats this perturbatively, and also many other things perturbatively, because at that time couldn't do large-scale computations. But we decided to look at this part. So the positive energy projected Dirac-Coulomb Wright equation. So we solved it. And for H2, H3 plus helium, first excited a singlet. And we had some experience in the perturbative computations, so we decided to compare the results. All the digits are significant, so converged in our work. And in nano-Hartree, these are very large, especially for helium ground state. So, okay, we were looking for possible bugs and so on. So these epsilon is from the literature. So precise expectation values of the bright polyhamiltonian. No, sorry, here, this is the DC, Dirac-Coulomb Hamiltonian Foley-Wightson perturbation theory. But if we add DCB, then that's the expectation value of the bright polyhamiltonian. So large deviations. So we go back to the theory and realize that, okay, Zuher derived alpha to the cube correction. This is due to the Coulomb ladder contribution to the positive energy states. And if we add this to the energy, or the perturbative and relativistic energies are almost on top of each other, we still see a deviation for helium. And Zuher stopped at alpha to the 3 order. But Pakutsky and Pukalski computed, but it's not separated in the same way as in Zuher's computation, but we could identify the non-radiative corrections, which also include bright, and we took the value that corresponds to after cancelling divergences, and they are in the same order of magnitude. So we could solve this positive energy projected Dirac-Coulomb equation for different alpha values. So we could check the alpha dependence of the energy. So we solved it to different alpha values. Alpha 0 is the recommended co-data value, and fitted a polynomial to the alpha dependence of the energy. The deviation is shown here. It turns out that we reproduce the regularized literature data of leading order relativistic correction to sub-nano-Hartree precision without regularization, just with using plain ECGs in a variational computation, which means that these difficult operators that appear in the PT expressions are included in the variational procedure, and the basis function. So the basis function coefficients are allowed to relax and can capture these difficult things. We can have also C3, which corresponds to alpha to the 3rd. Now I work in atomic units, so E Hartree, so it's in natural units, it would be M alpha 5. And this is Zuher's result from 1958, and this is our fitted value. See if we divided the difference with this delta R12, and this brings the different systems really to the same plot, to the same scale. We also get the C4 coefficient, so the 4th order. This in natural units M alpha 6, of the DC plus problem. The observation I would like to make here is that by looking at this ratio for the physical value of the fine structure constant, we get 10% for helium, but we get 50% for beryllium, which is large. So that the lesson we learned from this, we did resummation only for part of the problem, but for this part of the problem indicates that higher order non-radiative, I call them relativistic corrections, are increasingly important beyond z equals 2. Okay, and with this outlook, I would like to thank you for your attention. And
thank you very much. Is there questions? Yeah. Back. For change.
Yeah, I have a comment at the question. The comment is that I talked to Professor Sucher about this issue, and he told me that after emigrating from Europe to America, he changed his name from Sucher to Sucher. That's the comment.
Okay, thank you.
And the question is, could you point out a place where you drop the continuous spectrum? Because you are working basically continuous, the four-body Hamiltonian has a continuous spectrum, and the only mathematically meaningful numbers are positions and width of the Feshbach resonances, which of course are well defined mathematically for the continuation of the resolvent. But you don't have this. So somehow you are computing the positions defined, as I said, or you have some kind of other definitions of the specific energies in the continuous spectrum.
Which computation you are referring to? The relativistic?
No,
H2.
Non-relativistic calculations for
the EF state results.
Okay. But anyway, it doesn't depend on the state. Any state above the dissociation is in a continuous. So somehow you neglect it completely. But mathematically, the only meaningful numbers are the ones I told you, positions and width of the Feshbach resonances.
Okay. Yeah. So the way we did this, I agree. It's a trick. That if you look for long-lived resonances, then the life, so the imaginary part of the energy, I think in terms of complex coordinate rotation, is very small. So we got a parametrization as a result from this stabilization technique like optimization. And we did a complex coordinate rotation computation to get the position and the width. And the width was very small. It was smaller than our
errors,
numerical uncertainty.
So the answer to all the calculations are with rotated Hamiltonian?
No. So this optimization, because I need to minimize the energy to fine tune the parametrization. So this was optimization of the real. I selected. So I put a threshold, an energy threshold, and I minimize the energy with respect to this threshold. And I of course saw that states are falling into the continuum. And then I looked at the next state, and it was so the energy here stabilized. And for these plateaus, I repeatedly did CCR, so complex coordinate rotation computations, and looked at the real and imaginary part of the energy. And the real part was stable, and the imaginary part was numerically zero, double precision.
So maybe the imaginary part was eliminated by using the finite basis set, basically, because if you use arbitrary basis, then you would go down arbitrarily.
No, but I mean, in the complex coordinate rotation technique, you get the proper behavior. It's two things. One is about the parametrization of the basis, I guess, and then do the computation. The complex variational principle is, I mean, I haven't found it really practical for optimizing the energy, but perhaps it's possible to reformulate it somehow. I don't know.
Okay, and I understand that's of course difficult subject to optimize the rotated. I can rotate the Hamiltonian. Can you give it to further?
So I thought it was very insightful how you determine the electronic states that you need to keep outside those that you need to make the mass correction or this mass adaptive function. But so you basically you take a state and you see whether it contributes to this effective mass, and then you, on that basis, you decide whether you should keep it in the states that you couple. Is that the way to proceed, or,
No,
how,
no,
how do you get to the interacting states?
So,
You have the
so
far
I
away.
make an assumption. Say I kind of, so to get, say, a GK state. Let me, because then, yeah, okay. So I can decide. So I look at the Vibronic problem. So I need to look at only the sigma G plus. So get around it. And I try to increase my subspace. So okay, I had a single state computation, then I do a 2-state computation, I do a 3-state, and I look at the results, how they converge, and also, I mean, the size of the correction. So here, if I do a single state EF computation, then the mass correct, so the Vibronic mass correction is 480 times the electron mass. And that indicates that probably perturbation theory is not.
Yes, I understand, but so is there a recipe now to get the relevant states without having to systematically add, because there's a very large number in the end.
So the fundamental requirement is that in the relevant, over the relevant nuclear coordinates, you need to have a gap from the remaining electronic states. And this becomes a problem here because there are many more. It's not plotted here. So the increasing density of states here, and it's really a problem where to cut. So I look. So it's EFGKHH S5 S6 shown here. So the corrections got smaller as I included 2 more states. But okay, I get corrections also to these 2 states not shown here. And they are sometimes large because there are states close to this S6, and then the density of electronic states becomes very large. And but this problem is, I've told to electronic structure theorists, and this problem is known also to them, and they have some recipes, but it's very similar to my recipe, is that if I'm interested in this range, then perhaps the correction to this S6 is not so important, or S7 or S9 or S8, and just think like that and focus on this. So, but this is a fundamental problem.
The reason, one of the reasons why I ask is if you go to the H bar state and then you were to do the calculation in HD, you would find that the B bar state, which has symmetry, is there, would suddenly be the dominant contribution. And whether there is a general way to pick all these.
I mean, look, so I would look at what Polniavich did, and if the results are reasonably good but not sufficiently accurate, then I would add the PT corrections. So these corrections are expected to be small. So if these corrections are large, coming from the inclusion of this term, then that's an indication that you need to add more states, or you need to go to higher orders in the perturbation theory. But that's
okay. Thank you.
I would have comments to both parts. The first comment that when you apply this in non-adiabatic perturbation theory, which is a very good approach, but there's a comment to all of you. So when you have when you consider interaction of 2 atoms from the large distance, you always assume there is some interaction potential, some effective interaction potential. This is very natural. But what is the conclusion for the perturbation theory? That there is also correction to the mass. So if you want to describe accurately, for example, the scattering length, if you have 2 cold atoms and try to calculate scattering length, scattering at the small energies, one has to include not only the potential, the correction to the potential, but also correction to the mass. So the mass is not like the mass of the atom, mass of ion. There's some correction to the mass, the parallel mass, to the I don't know how to describe this, but so in fact, so not only the potential changes of the large because of the interaction between atoms, but also the masses, effective masses. So to describe the scattering of the interaction of the large distances, one has to also account for masses. It's interesting. It is not, you will not find this in the textbook somehow, but if you want to describe it more accurately, one has to take into account the mass. My comment to the second is more direct. When you started from Dirac-Coulomb Hamiltonian, these are very good results. But the problem is, nobody so far formulated QED theory on the top of Dirac-Coulomb Hamiltonian. There is no formulation. What is the conclusion for this? If there is no formulation of a QED theory on the top of Dirac-Coulomb Hamiltonian, then whatever you calculate, you cannot give uncertainties to your result. You can always compare to someone else, maybe to an experiment, but your calculation is not an independent calculation in the sense that you cannot give what is your uncertainty. Because if there is no QED theory built on this, you don't know how to add the QED correction. It is not just a plain sum. I calculate Dirac-Coulomb and I calculate QED. No, because since there is no QED theory built on this, we don't know how to incorporate QED on the top of Dirac-Coulomb Hamiltonian, whatever way you calculate this. So it's very good that one is able to calculate some corrections in the easier way, but how to calculate other corrections on the top of what's done, it's impossible. We don't know how to do it.
We are thinking about this, and I took this as a challenge, Christoph. And the reason why I took this seriously, not just as a game, is that because we have this beta sulfate variation. But I mean, if an experimentalist asked for help, I wouldn't recommend. I mean, wouldn't do this. I would do. I have the implementation of the level of 5, and I could offer to do that. But so this is really a theory challenge. Yeah, I was already happy to see this. This was also not available in the literature, and so we've learned already a lot. And maybe we will stop at some point. But I mean,
you may go on for a bit. Once more, Bogomil?
Yeah, I have a comment to Krzysztof's comment about
This is for the coffee break.
about the masses. Actually, we computed the scattering length for helium-helium scattering, and if you do atomic masses and nuclear masses, you have a very different results. But we found that if you do distance-dependent masses for the helium scattering, the atomic masses provide an excellent approximation. So for such a weakly interacting system, the atomic masses can be used for the scattering calculation of the weakly interacting system.
Okay, thank you. I have just a very practical question. You see, for the inner well E states, you get accuracy of 10⁻³ wave numbers, yeah, and for the H, you get 0.1 wave number, big discrepancy, and because the density of states is much higher and it's more complicated up there. And so, if you go to the F outer well, would that be equally accurate as the inner well? Because density is more or less similar.
I see a chance for the F outer well from 4-body, but as Bogomir pointed out, we are fishing in the sea of states. So, and this is the reason why I started to look at the perturbative approach, but that that has some other difficulties. So we will see.